want to start this video by talking a little bit about the definition of a normal extension. So let's think back to how this was first defined in Dummett and Foote. In section 13.4 on page 537, if K is an algebraic extension of F, which is a splitting field over F for a collection of polynomials, f of x in f bracket x, then K is called a normal extension of F. And the question I want to ask is something I dodged at the time when we first talked about this. What's up with this phrase, a collection of polynomials? Right? Like, why is that important? Well, if K is a splitting field for a finite collection of polynomials in f bracket x, say f1 of x, f2 of x, up through fn of x, what does that mean? K is an extension of F in which each one of these fi of x splits completely into linear factors, and no proper subfield of K has this property, that each one of these polynomials splits completely into a product of linear factors. But in that case, K is a splitting field for the single polynomial given by their product. Right? So the product is going to split into linear factors if and only if each one of these polynomials in our collection splits into a product of linear factors. I mean, one way to think about that is, what is this splitting field? You take all of the roots of each of these polynomials, and you take the field generated over F by all of those roots. But all of the roots together of all of these polynomials, these are the roots of the product of all of these polynomials as well. So, yeah. Okay, so if you have a splitting field over F for a finite collection of polynomials, it is the splitting field over F for one polynomial. But for infinite extensions, there really is a difference. So, for example, if you take K to be field generated over Q by square root of 2, square root of 3, square root of 5, square root of 7, square root of 11, square root of P for each prime P, this is a splitting field over Q for a collection of polynomials. What collection? The polynomials x squared minus 2, x squared minus 3, x squared minus 5, and so on. This infinite collection of polynomials in Q bracket x. But K is not the splitting field over Q for a single polynomial. You can see that just for degree reasons. Okay, so Dummett and Foote use this definition of normal that involves a collection of polynomials. I think that the entire time this is hinting towards this use of this term for infinite extensions, but they don't address that really up front. So what I want to talk about next is that what Dummett and Foote call a normal extension is not the same thing as what everyone else calls a normal extension. It seems that many, many other references define a normal extension in a different way. So I'm going to pause and erase, and I'll give you this other definition of a normal extension, and then I'll justify why these two definitions are allowed to coexist in this way. We just reviewed the definition of a normal extension given in Dummett and Foote. How do other references define a normal extension? Here's the definition that's in Conrad's, the Galois correspondence notes. An algebraic extension K over F is a normal extension if every irreducible polynomial with coefficients in F, which has a root in K, has all of its roots in K. That is, every irreducible in f bracket x with a root in K splits completely in K bracket x. So I was a little confused when we first got to the part of Dummett and Foote where they define a normal extension, because if you asked me what is a normal extension, this is the definition that I would give. I think that if you look around in other places, this is a more standard definition for what it means for an algebraic extension to be a normal extension. Okay, so what's going wrong here? now we've given two different definitions for normal extension. And you shouldn't panic. It's okay. And what I mean by it's okay is theorem 3.18 in Conrad's The Galois Correspondence Notes says for a finite extension K over F, these two notions of normal are equivalent. K over F being normal, in this sense, every irreducible in F bracket X with a root in K splits completely in K bracket X, is equivalent to saying K is the splitting field over F of a polynomial in F bracket X. Okay, so things are a little subtle for infinite extensions. We don't need to talk about that here, but that's something that maybe you'll be interested in and want to read more about. But from now on, in my mind, when I say normal extension, what I mean is an extension with this property that every irreducible in F bracket X with a root in K splits completely in K bracket X. So let me just point out that in this theorem, there's no separability assumption. So you can talk about a normal extension here that is not separable. And you can talk about being the splitting field of a polynomial that's not separable. Like this theorem doesn't require anything about separability. I don't want to do the proof here, partly because we don't need it right now. I encourage you to go and look at it. But another reason is that the proof uses something that we haven't seen yet that we may see at the very, very end of the course. So it uses this result that symmetric polynomials are polynomials in the elementary symmetric polynomials. So I'm not expecting you to know what that means at this point. You'll never need to know what that means for an exam, but this is something that we may talk about at the very end of the course. This is a corollary. If this is closely related to corollary 31 in section 14.6 and the remark that follows it, that there's first some statement about symmetric functions and elementary symmetric functions, and you can deduce this statement about symmetric polynomials and elementary symmetric polynomials, and some of that is worked out in the exercises for section 14.6. Okay, so now that I feel like we've cleared up some of these issues around the definition of normal, I want to go back and revisit another definition that we talked about from Conrad's notes at the beginning of our discussion of Galois theory. Let's recall definition 2.1 from Conrad's The Galois Correspondence Notes. The roots of a common irreducible polynomial in F bracket X are called F conjugates. So let me just point out an issue that sometimes confuses me when I'm putting together my notes. Dummett and Foote refer to an arbitrary field extension almost always as K over F. And in Conrad's notes, it's almost always L over K. So you just have to get straight, like, which field is which, depending if you're bouncing between different references. Okay. Now I want to come to a definition in Dummett and Foote. Let's say that K over F is a Galois extension. If you have some element alpha and K, you can apply the elements of the Galois group to alpha and see what you get. So these elements, sigma of alpha, where sigma is some element in the Galois group of K over F, are called the Galois conjugates, or just the conjugates of alpha over F. And okay, this is potentially a little confusing, but we'll see that it's okay, right? So this is conjugates, means Galois conjugates. Here, conjugates are roots of a common irreducible polynomial. Okay, conjugate for fields. So if E is a subfield of K containing F, the field sigma of E is called a conjugate field of E over F. So this is actually written in Dummett and Foote as the conjugate field, but it depends which sigma you take. For different sigmas, you might get different conjugate fields. So just remember, like, what is sigma? It's an automorphism of K fixing F. So because you're getting an isomorphism from K to K, it has to send E to a subfield of K that is isomorphic to E. So it doesn't necessarily send E to itself, but it sends E to another subfield of K that contains F. Okay, and a corollary of this proposition 13 star that we proved is that if K over F is a Galois extension, and if alpha is in K, then the distinct Galois conjugates of alpha over F are precisely the roots of the minimal polynomial of alpha over f. Right? So what did we see? We took this alpha, we applied each element of the Galois group of k over f to alpha. We took the distinct elements that occurred in that collection, and we saw that those were exactly the roots of this polynomial p of x, which we saw was m alpha f of x. So here this matches up really, really well, that the Galois conjugates of some element alpha in K in a Galois extension are exactly the roots of this irreducible polynomial, the minimal polynomial of alpha over f. Okay, so it should not bother you that these two different concepts both get called conjugates because they match up in the setting of a Galois extension. And in an extension that's not Galois, we would not talk about the Galois conjugates of an element. Okay, what are we seeing? We're seeing that the Galois group of a Galois extension k over f acts transitively on the roots of the minimal polynomial of alpha. So what does that mean? If you have any root beta of the minimal polynomial of alpha over f, there exists some element sigma in the Galois group that sends alpha to beta. So now this is going back to a question that we asked a few lectures ago. When can you always find some automorphism of k fixing f, sending one root of an irreducible polynomial to another root of an irreducible polynomial? Okay, so the last thing I want to say here is that we have proven that a Galois extension is normal and separable. So that means that if we find even one irreducible polynomial in f bracket x that has a root in k, but does not have all of its roots in k, then k over f is not a Galois extension.